the power of A decreases from first to last term, whereas the power of B increases from first term to the last term. If I take R as 1 here, then it is KC1 plus KC0. So which can be written as K plus 1 C1. Index is nothing but power. So the power is 2. So if we expand this, then the number of terms in the expansion is 3. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am, Vidhyaashram School of Excellence, Mysore. So here in this session, we are going to take up the new chapter, Binomial Theorem. So this is the expansion of binomial term when you have the highest powers in terms of 20, 100. So we have an expansion using the formula. So we'll study that, we'll prove the theorem and we'll take up problems related to binomial theorem. Now let us see the statement of the binomial theorem. So we have state and prove binomial theorem. For any positive integer n, a plus b whole to the power n is equal to nc0 a power n, nc1 a power n minus 1 b plus nc2 a to the power n minus 2 b square plus ncn minus 1 8b to the power n minus 1, and the last term is ncn b power n. So you can clearly expansion of a plus b whole power n. So if I take this as a plus b whole power 1, so this is a plus b itself. And if I take this as a plus b whole square, we know the formula, that is a square plus 2ab plus b square. And if I expand this a plus b whole cube, then this is a cube plus 3ab into a plus b plus b cube. So this is already an algebraic identities which we have learnt. Now if the power is more than that, how to express this? So when the powers are more, the binomial term can be expanded in this form using the combination and the terms with a and b. So you can clearly see here nc0, nc1, nc2, ncn minus 1 and ncn. They are all called as binomial coefficients. When you substitute the value as n there, obviously you will get a numerical coefficient. Now if you observe the term a here, the power of a goes on decreasing until the last term. See, a power n, n minus 1, n minus 2, and here it is a power 1, and here obviously it is a power 0. So anything to the power 0 is 1, so that's why we have not mentioned there a power 0. Now if you observe the power b, the power of b increases. So here there is no b, means it is obviously b to the power 0. Now here b power 1, b square, b to the power n minus 1, and the last term is b power n. So these are the observations in the expansion so that it is easy to remember the binomial theorem statement. So we can see the coefficients start from nc0 to ncn, which are called as binomial coefficient, and the power of a decreases from first to last term, whereas the power of b increases from first term to the last term. So this statement is called as the binomial theorem. So here we use the proof of mathematical induction to prove this result. So what is this to mathematical induction proof? So first we will take the value of n for some values, and then we'll take it for n is equal to k values, and then we'll prove for the next integer. If it is true for all the given integer, then obviously the statement is true. Now let us start proving the result here. So now let me consider this equation as p of n. So I'm considering this equation as p of 1. So let us prove the result for n is equal to 1. Then p of 1. So here p of 1, the entire equation, the left hand side and the right hand side. So a plus b whole to the power 1 is equal to 1c0 a to the power 1 plus 1c1 a to the power 1 minus 1. We can't go 1c2 because r cannot be greater than n. So we'll stop here. So a plus b whole power 1 is a plus b. 1c0 is 1, a power 1 is a. So here we have also b. Next 1c1 is 1, a power 1 minus 1 is a power 0, which is 1, and into b, b. So therefore here my left hand side as well as the right hand side are equal here. So therefore we'll conclude P of 1 is true. Now since P of 1 is true, I'll assume the result let it be true for k values. So now assume the result is true for n is equal to k values. So that means P of k is equal to a plus b whole power k is equal to kc0 a power k plus kc1 a power k minus 1b plus kc2 a power k minus 2b square, and the last term kck b power k. So let me take this as equation 2. Now let us prove the result for n is equal to k plus 1 values. So to prove for n is equal to k plus 1 values, so here consider a plus b to the power k plus 1. So consider a plus b to the power k plus 1. This can be written as a plus b whole power k into a plus b. So using the theory of indices, k plus 1 can be separated as a plus b to the power k into a plus b to the power 1. Now here we have an equation 2 which is a plus b power k. So for this equation, so let us multiply a to the equation once and then we'll multiply b to the equation. So using 2, so here using equation 2, so instead of a plus b whole power k, we can consider this entire expansion. So for that expansion, we have a product a plus b. Let us multiply a to this equation. So then this becomes kc0, a into a power k is a to the power k plus 1 plus kc1, a power k minus 1, a power 1 becomes a power k, b will remain same. Next we have kc2, a power k minus 1 into 1 plus 1 is a power k minus 1, b will be same, plus etc. The last term kck, a b power k. So we are finished with multiplying a. Now let's multiply b to the given expansion. So plus kc0, a power k, b. Next, kc1, a power k minus 1, b square, plus kc2, a power k minus 2, b cube. And the last term is kck, b power k plus 1. Now when you multiply a and b to these equations, so this is what we will get. Now here, observe we have few common factors. So let us leave kc0 and kck, the last term, as it is. Now consider these terms, a power kb, a power kb. So if we take this as a common factor, we will get kc1 plus kc0. Let me write the first term as it is. That is kc0, a to the power k plus 1 plus. Now I am taking a power k into b outside the factors, then I'll get kc1, kc0. So I can write this as kc1 plus kc0. Next I'll take a power k minus 1 b square here, a power k minus 1 b square here. So if I take a power k minus 1 b square as a common factor, then I'll get kc2 plus kc1. kc2 plus kc1. So similarly, I can take the remaining common factor and let us write the last term kck, b to the power k plus 1. So now using the property of combinations, we know that I'll write the property kc0 is same as k plus 1 c0. And similarly, kck is same as k plus 1 c k plus 1. Because what is kc0? It is 1. So whatever the value you replace with k and with 0 as r, you will always get 1. Similarly, kck value is also 1. So if you change k plus 1, it doesn't alter the values. It's one and the same. And also we know that KCR plus KCR minus 1 is equal to K plus 1 CR. So we have proved this result in the chapter permutation and combination. So now we observe here, if I take R as 1 here, then it is KC1 plus KC0. So which can be written as K plus 1 C1. So using all these property in the given statement here, this can be written as K plus 1 C0 a to the power K plus 1. And here this can be written as K plus 1 C1 a power K B. Next, this can be written as K plus 1 C2 using this result. Put R is equal to 2 here, you will get the same equation. So a power K minus 1 B square plus the last term can be written as K plus 1 C K plus 1 B to the power K plus 1. So what is the equation we have taken here? This is A plus B whole to the power K plus 1. Now observe my equation 1. Observe equation P of n here. So wherever n we have, so that is taken in the form of K plus 1. So here, so nC0 is K plus 1 C0. A power n is A power K plus 1. Now here A power n minus 1 is K plus 1 minus 1, which becomes K. So that means the result is true for K plus 1 values also. So therefore we can conclude here P of K plus 1 is also true. So it does not changing the statement, original statement. So this is also true. So therefore, by mathematical induction method, so the result P of n is true for all n belongs to n. So that is set of natural number. So whatever the values you take under n, so the result is true. So this is the proof of binomial theorem. Now let's see some of the observation we'll study in the binomial theorem. So if we see the expansion of a plus b power n, there will be having n plus 1 term. For example, I'll take a plus b whole square formula. What is a plus b whole square? It is a square plus 2ab plus b square. So the index is 2 here. Index is equal to 2. But what is number of terms? So number of terms is 2 plus 1, which is 3. So index is nothing but power. So the power is 2. So if we expand this, then the number of terms in the expansion is 3. So therefore, in the expansion of a plus b whole power n, if the power is n, then the number of terms in the expansion is n plus 1. Next, the coefficients of NCR. I already told you the coefficient NC0, NC1, NC2 until NCn, they are called as binomial coefficient. And also I told you the indices of A go on decreasing. That means the power of A go on decreasing until the last term, and the power of B goes on increasing by 1. Each time it is B, B square, B cube, B power 4 until B power n to the last term. Observe that index of A, index of B is equal to n. Look at the statement here. So what is the index of A here? It is n minus 1. What is the index of B? That is the power of B, 1. Add this, it is n. So in each term, it is n only. Let's check for the another term. What is the index of A? N minus 2. What is the index of B? Add this. What is the value? N. And what is here? 1 plus n minus 1. So it is n. What is here? N. And what is here? It is n. So in each term, the index of A and B, index of A plus index of B is always equal to n. Next is some properties of combination which we have already studied. NCR is NCn minus R. NC0 and NCn are same, whose value is 1. And also NC1 is nothing but NCn minus 1. So all the result will give you the same value here. So here it is same. The value of the combination will be same. So here the value is equal to 1 for both. Here the value is equal to n for both. Now, let us take few problems here. Expand each of the expression x plus 1 by x whole power 6. So, we need to expand this expression here. So, let us take what is a, x, b, 1 by x, n, 6. So, then how many terms are there? The number of terms is 7. So, let us start with nc0. So, using the statement 6c0 a power n, so x power 6. Next, 6c1 x power 5 1 by x. 6c2 x power 4 1 by x whole square. 6c3 x cube 1 by x whole cube. 6c4 x square 1 by x whole power 4. Next we have 6c5 x 1 by x whole power 5. The last one 6c6, there is no x, so 1 by x whole power 6. Now the value of 6c0 is 1. So the first term is 6 power 6. The value of 6c1 is 6. We have x, this for x power 4. Now 6c2 and 6c4, they are one and the same. Because 4 plus 2 is 6. So we can write this as 6 into 5, 2 into 1. So the value is 15. So the value of 6c2 and 6c4 will be 15. Now let's calculate 6c3. 6c3 is 6 into 5 into 4 divided by 3 into 2 into 1. So 20. The remaining and all we can directly substitute. 6c2 we got it as 15. And here we have x square get cancelled. So it is x square. The next thing is 20. So x cube cancels. So just 20. The next term is x square in the numerator and x power 4 in the denominator get cancels. So it is 15 into 1 divided by x square. The next term is 6c5. 6c5 value is same, 6. 6c1 is same as 6c5 because 5 plus 1 is 6 and nc1 if we have it is n. So therefore it is 6. So now here x cancels with the denominator x power 5. So therefore it is 1 by x power 4. The last ncn is 1. So we have 1 by x power 6. So this is the expansion of the given binomial term. Next one, 2 by x minus x by 2 whole power 5. So let's take this. We can write this as 5c0. Here a value is 2 by x. B value is minus x by 2. So next, 2 by x whole power 5 plus 5c1 2 by x whole power 4 minus x by 2. Next, 5c2 2 by x whole cube minus x by 2 whole square. Next, 5c3 2 by x whole square minus x by 2 whole cube. Next, we have 5c4 2 by x minus x by 2 whole power 4 plus 5c5 no 2 by x minus x by 2 whole power 5. So 5c0, 5c1 is 5. We'll calculate 5c2 and 5c3. It will be the same. 5c4 is 5. 5c5 is 1. So 5c2 is same as 5c3, which is 5 into 4 into 2 into 1. So which is 10. Now we'll calculate here. 2 power 5 is 32 divided by x power 5. And 5c1 is 5. 2 power 4 is 16. So here we have minus x. So we have minus 1 by 2. Next we have 5c2 which is 10. 2 cube is 8. So we can cancel 8. Here we have x cube. So x cube and x square get cancels here. So we have 1x in the denominator. Again we have 1 by 4 here. So next we have 5c3 which is again 10. So 2 square is 4. So x square and 1x cancels. So therefore it is minus x divided by 8. And here we have 5c4, which is 5. So 2 here, and here we have x power 4 by 16. The last one is 1. So minus x power 5 divided by 32. Now it is 32 divided by x power 5. 2 1s are 2 8s are 5 8s are 40. So minus 40. Next we have 4 1s are 4 2s are. So plus 20 by x. Next we have 4 1s are 4 2s are 2 1s are 2 5s are. So we have minus 5x. Next we have 2 1s are 2 8s are. So we have plus 5 by 8 x power 4 minus x power 5 by 32. So this is the expansion. Next question. Using binomial theorem, evaluate the following. So we have 96 whole cube. So the number can be expressed as 100 minus 4 whole cube. Now using binomial theorem, the value of A is 100. The value of B is minus 4. So let us expand 3C0 100 cube plus 3C1 100 square minus 4 plus 3C2 100 minus 4 whole square plus 3C3 minus 4 whole cube. Now here 100 cube, 3C1 is 3, 3 4s are 12, so it is 12, 0 0 0 0. Again 3C2 is 3, 3 into 100 300, 300 into 16, so which is 4800. Next 3C3 is 1, so minus 4 cube 64. So evaluating this, we'll get 8 8 4 7 3 6. Next one, 102 whole power 5. So this can be expressed as 100 plus 2 whole power 5. So now this can be written as 5C0 100 power 5 plus 5C1 100 power 4 into 2, 5C2 100 cube into 2 square, 5C3 100 square 2 cube, 5C4 100 2 power 4, 5C5 2 power 5. So if you expand this using the binomial coefficient and multiply the 100 and 2's, the final value will be so that is equal to 11,040,80,8032. So this is the value you will get when you expand 102 using binomial expansion. So the next one is, which is larger, 1.1 whole to the power 10,000 or 1,000. So let us write this 1.1 whole to the power 10,000 as 1 plus 0.1 to the power 10,000. Now this can be expressed as 10,000 C0 1 to the power 10,000 plus 10,000 C1 1 to the power 9999 and 0.1 to the power 1 plus etc. So if we expand this, here we'll get 1. 1 into 1 power 10,000 is 1. Now 10,000 C1 is 10,000 into 0.1 is 1,000 again. So plus etc. So this is already greater than 1,000. So therefore 1.1 to the power 10,000 is greater than 1,000 clearly. Next question, find a plus b whole power 4 minus a minus b whole power 4. Hence evaluate root 3 plus 2 root 2 whole power 4 minus root 3 minus root 2 whole power 4. Let us expand this. So a plus b whole to the power 4 is equal to 4c0 a power 4 plus 4c1 a cube b plus 4c2 a square b square plus 4c3 ab cube plus 4c4 b power 4. Next we have minus b in the place of b. So the same expansion can be written as 4c0 a power 4, 4c1 a cube b, 4c2 a square b square, 4c3 ab cube, 4c4 b power 4. Now we need to subtract this, so we'll change the sign. Minus, plus, minus, plus, minus. So the term which is common get cancels with the opposite sign. A plus b whole power 4, a minus b whole power 4 is equal to cancels. So here these two terms cancels and these two terms get cancelled. So we are left with 2 times 4c1 a cube into b. Next 2 times 4c3 a into b cube. So here 4c1 and 4c3 is 4. So 2 4s are 8, 2 4s are 8. So this is 8 a cube b plus 8 a b cube. So what is common factor here? 8 is common factor, a is common, b is common. So the remaining is a square plus b square. So this is the value we'll get when we expand this. Now if we apply this result here, so root 3 plus root 2 whole power 4 minus root 3 minus root 2 whole power 4, this is equal to 8 into, so root 3 root 2 into 3 plus 2 because a square b square. So 5 8s are 40, root 3 into root 2 is root 6. So therefore the value is 40 root 6. Next one, show that 9 to the power n plus 1 minus 8n minus 9 is divisible by 64. So now here 9 to the power n plus 1 can be written as 1 plus 8 to the power n plus 1. So if we expand this using binomial theorem, we will get n plus 1 c0. Since we have the first term as 1, so we can leave a, we can just write b. N plus 1 c1 8. N plus 1 c2 8 square. So like that we have n plus 1 c n plus 1 8 to the power n plus 1. So this is the expansion we'll get. If we take a as 1, so how many times you write a? It is 1 only. So now here 9 to the power n plus 1, n plus 1 c0 is 1, and here n plus 1 c1 is n plus 1 into 8, and here if we take 8 square as a common factor here, we'll get n plus 1 c2. The next term will be n plus 1 c3, 8 cube becomes 8. And the last term here, if I remove 8 square here, that means minus 2, n plus 1 c n plus 1 becomes 8 to the power n minus 1. Now here this is some integer because all of them will be a value. 8 square is 64 here. So 9 to the power n plus 1, 1 plus 8n plus 8 plus 64 into some integer value. And here if we shift all these towards the left hand side, we'll get 9 to the power n plus n minus 8n minus 9 is equal to 64 into some integer value. It's a product of 64 with some integer. So therefore, which means 64 divides 9 to the power n plus 1 minus 8n minus 9. So this clearly indicates that this 9 to the power n plus 1 minus 8n minus 9 is divisible by 64. The next one is we have proved that summation r is equal to 0 to n 3 power r NCR is equal to 4 to the power n. Now let us consider the left hand side. If we take the summation as r is equal to 0, the first thing is we get NC0 3 power 0, NC1 3 power 1, NC2 3 power 2 plus etc. We have until r is equal to n, NCn 3 power n. So now using the binomial theorem, so we can see the power of 3 is increasing. So let us consider an element a here where a value is 1. So if we consider this expansion as 1c0, 1 power n into 3 power 0, nc1, 1 power n minus 1, 3 power 1, NC2, 1 per n minus 2, 3 square, and the last term as NCN, 3 per n. So the very first value is 1 here. So here, if we reduce this in the binomial term, this is A and this is B. So here it is 1 plus 3, that is A plus B whole to the power n, because the coefficient and the power is n. What is 1 plus 3? That is 4 to the power n. So it is the right hand side of the equation. Hence true. So in today's session, we have learned the statement of the binomial theorem, the proof of the binomial theorem, and the application of binomial theorem in terms of problems. I'll meet you in the next session. Until then, keep watching, keep learning, and keep exploring. Thank you.